Alright, welcome to another video on line integrals. In this video, we're going to be solving the following example. We're given the following line integral of the function 2x, and now what we're going to do is we're given this curve that is actually just the union of two different curves. So what they tell us is that C1 in this case is just a parabola, so it is defined by this function, and the curve C2 here is just a straight line segment from the point 1, 1 to the point 1, 2. Now at this point we need to introduce a concept which is the concept of linearity of line integrals. So basically, if your total curve is expressed as a union of different curves, so basically it is just a combination of different curves, then all you need to do to find the total line integral is just to add up the contributions by each of those curves individually. So in this case what we can do is we can start off with the first one. So we say, okay, so this curve is represented by a function y as a function of x. So that means that x is just going to be an independent variable, which means that we can just make it equal to itself. And now the limits of integration on this curve are just going to be the limits on x. So basically the curve is extending from 0 to 1, which means we're going to have the following. Just like that. And now what we're going to do is we're going to try and integrate. But before we do that, we also need to find the element ds. So the element ds in this case is going to be defined. We have our parameter is x. So that means that our increment here is going to be with respect to x. So we're going to have dx over dx. Remember, we put the parameter at the bottom. dy over dx squared. And it turns out that this term is just going to become 1 because we have x with respect to itself, which just becomes 1. So we're going to have ds equals to dx square root of 1 plus this. So this is just going to be 2x. And then if we square that, that becomes 4x squared. Alright? And now all we need to do is to put that back into the equation. So for C1, we're going to have the following. We're going to integrate from 0 to 1. We're going to put all the values into here. So we only have x, so basically just put x into there. 2x. Now ds is going to be this element right here. So this is going to be square root of 1 plus 4x squared times dx. And now in order to do this integral, what we're going to do is use substitution. So let u equal to 1 plus 4x squared, such that du becomes 8x times dx. So that means that if we multiply this by 4, so let's just do it here. Let's divide by 4 outside, multiply this by 4, so it becomes 8x dx, and then we have the square root of 1 plus 4x squared. So this is going to become the following. We're going to have square root of u times du. And now if we integrate this, this becomes 1 over 4. This becomes u to the power 3 on 2. And then divided by 3 on 2. So the 2 is going to come to the top there. And then we're going to substitute for x before we actually put in the limits of integration. So now we're going to have 1 over 4 times 2 over 3. And right here we're going to put this back in. So we have 1 plus 4x squared to the power of 3 on 2. Evaluated from 0 to 1. So let's see what we get. Well, this is going to become 1 over 2, so 1 over 6. And we're going to have, we put 1 in here, that becomes 5 to the power of 3 on 2. And then if we put this here, that just becomes minus 1. So that's going to be the first integral. So that is with respect to the curve 1. And let's see if we can simplify this in any way. So basically, we're going to have 5 to the power of 3 on 2, which is the same as 5 times 5 half, which is 5 square root of 5. So we can write this as, let me just erase this here very quickly. This is just going to become 5 square root of 5 minus 1 over 6. So this is the first integral, the first line integral that we evaluate. Now for the second one, what we're going to do is we're going to grab this line segment here, and we're going to evaluate the line integral with respect to that line segment. Now, we already discussed how for straight line segments we normally use this kind of equation here, this parameterization, but in this case we have a line that's going straight up, so there's actually a much easier parameterization we can perform. So now let's do C2. We have a straight line segment that goes from this point to that point, but you notice that it is just a function, it doesn't really change with x, it just goes straight up. So actually I forgot to put the values in here. So what that means is that we can represent this by the function x equals to 1, because it is basically just a straight line of x going all the way here. And then we notice that, well, y in this case is just going to be an independent variable, because if x were a function of y, then y would just be equal to itself. So now we can treat y as the parameter. So we can say something like, okay, so the limits of integration here are going to be from 1 to 2, because that is essentially, if you flip this on its side, you notice that you have, these are the limits on y, and now you have a straight line which is a constant function in terms of y. And now what we're going to do is we're going to find the element ds for this curve. So ds is going to be equal to, now the parameter is y, so we have dy. We're going to have the square root of dx over the parameter dy plus dy over dy, which we know is going to turn out to be 1. So now we get dy times the square root of, okay, so let's differentiate this with respect to y. Well, it turns out that there's no dependency on y, so this becomes 0. This is 1, so this becomes dy. And now, if we grab our integral, C2, the function is 2x, we just replace x by whatever values here, so it turns out that this is going to be just 2 times dy, and now the limits of integration are from 1 to 2. So this one is pretty straightforward. We have 2y to 1, so this becomes 4 minus 2, which is equal to 2. And now that we have the two curves together, what we can do is we can say, okay, so the line integral for the whole thing is going to be the integral from C1 plus the integral for C2, and then the first one we found was 5 square root of 5 minus 1 over 6 plus 2. So this is our final answer. This is going to be the line integral for the whole curve involving C1 and C2. So that's a really important thing that we need to take note of. So because sometimes the curves that we're given is actually going to be split into different curves. So this is a really important formula that we need to know. And also sometimes you can simplify things by not having to use this kind of formula here for a straight line segment, but sometimes you can just think of a more suitable kind of parameterization such that it all reduces to a very simple expression.